Lightning Talk will be about solving type literals.
Yeah, hi. I'm going to talk about solving inequalities instead of inequalities on type-level natural numbers. So what do I mean by that? Let's say you have this code, the GADT on top, a vector with the length annotation, and we have the standard cons, and then concat. If you want this to type check, the GHC will ask, or without a plugin, you would be asked to show the equality that you see at the bottom. And using high school or primary school, depending on your country, you can solve that through axioms and come to a conclusion that well, they are syntactically equal. And so we've had a plugin that does this kind of things for quite some time, almost 10 years. Still maintained today, works on the to-be-released GC 9.12. It can show fairly complex equalities involving exponentiation. And the only way this works is because the thing you see on the right is the chosen normal form. Like there's many normal forms we could have picked when you involve exponentiation. But there was a straightforward algorithm that expands the left-hand side to the right-hand side. And rewriting works very well when you want to deal with equalities, but it did not turn out very well for inequalities. So inequalities were sort of bolted onto GHC typelist net normalized and never really worked well. So it never worked it could not show transitivity of inequality. It just didn't. It refuses to solve it. And also there were bugs. So if you turn on the current plugin, you can build a proof that false is equal to true. So that's very highly undesired. Somebody can probably turn this into an unsafe course. You might be wondering, like, why not use SMT, use Z3? So me and my colleagues, we work in a field with lots of exponentiation. So not polynomials, exponentiation. So the non-constants are in the exponent. And we found that Z3 chokes very quickly. We've tried other SMT solvers as well. They just don't like to deal with these non-linearities. So we had to do something else. So at QBlogic, we had a quite bright intern, Alexander Pokolitov. He built, I think, 4 plugins over the course of 20 weeks, including this last one. It will be if you've been using GC typelist net normalized, this will be its replacement. It has a new solver based, again, on rewriting, also, well, some interval arithmetic, and also Newton's method for root finding as a backup in case interval arithmetic doesn't work. So the solver is there as a library. The subset is currently only on GitHub. It has a SMT lib kind of interface, and we also use it in the plugin. It passed the complete test suite of GHC typelets net normalized, and it can finally prove all these things. So it can show transitivity, it can deal with other inequalities as well. That's the lemma 2. And it can finally move from inequalities to equalities. So if it knows that x is basically between 0, then it must be 0. Something that the previous plugin could never handle. Let's say before the end of the year, this plugin will be on Hackage, and it will also be made sound. The thing that Simon mentioned in the GHC update, we still need to apply the tracking of our used lemmas in a way. But yeah, that's what I wanted to say. And on to the next speaker, I guess, unless there's some questions.
Are there any questions?
Just want to say, very cool, Kristen.
All right, thanks.
Fantastic.
I don't have a for a Mac.
Oh, I have one.
We're trying to get my Mac set up here. While I do that, so this started out as a experiment on what it would take to actually be able to make GHC a really good strict language. Now, this is not how I would like to do that. But it was sort of, we started picking up a bunch of capabilities in that direction. We have all these runtime representations and what have you. And I would like to see if I could get Prelude to run that way. Let me switch my screen over somehow. Screen mirroring. Display settings, come on, just duplicate. Arrange on top of each other. To mirror hold option while dragging, we change this in current. Hold on. Apparently not good at this. All right. Are we good? All right. So I started experimenting with what it would look like if we could take, I apologize for the size of the font, let me try and blow that up. A standard class, let's start with something like eq, and make it runtime representation polymorphic. Now I can define equals and inequality just fine. But then I go to define the default definitions for those. And now here's where we're allowed to have runtime rep polymorphism starts to bite me in the butt. So we can only be runtime rep polymorphic in the result position of a function. So I can have a function that returns a runtime rep polymorphic result, because we can do that to because I just don't care to call it if I'm just going to blow the stack or something like that, right? That's the kind of situations where you might be able to do this sort of thing. I'm going to invoke it and it's going to call me back with the right registers, and therefore it's not my problem. Okay, that's sort of the trick. But but if I have to pass it, I don't know what kind of registers that is. An int rep is going to be an integer register, and adder rep is going to be something, some SIMD crazy thing, floating point register, what do you do? So what can I do? Well, I can punt the problem. I can make another class that's responsible for dealing with this, and then use default signatures to say, use that instead. That class doesn't know anything about my instances for eq, but it does know what my runtime representation is. Now what I can do is I can lift all the things from Prelude directly in, and then I'll make this eq rep thing. I have to make instances somewhere, though. Where do I put them? So the problem is something like this. Let's say I build this library, and then 2 people depend on my library. If they had to instantiate this class independently, locally, just because runtime reps are a big, nasty, infinitely long set of things, because you have tuple reps and stuff in there. If I need to be able to supply instances for all of the different possible runtime representations, I'm doomed. If 2 users came along and supplied the same instance. So where could I put them? Well, like if you go to a library called parsers, and parsec already existed, well, where would I put the instances for parsec? I could put them in the parsers library, or I could put them in an orphan instance package and then hope that people try to pull up the orphan instance package. But at least if I put it in an orphan instance package, people would know where to get it from a canonical location. But how do I put an infinite family of things into packages on a canonical naming basis on Hackage? That seems somewhat problematic. I can't take an infinite portion of the namespace. But what I can do is I can use backpack, which is kind of a weird choice, and this is the wrong choice, and this is going to point to why I want something better, but I'm going to use the only damn tool I have to do this. So what backpack is, if for those of you who are not familiar with it, is a form of like applicative functor, an ML term, applicative functor syntax for Haskell, where we can parameterize a Haskell package on another package. I have to brush really, really fast here, so I'm going to try and get to the point. And what I can do is I can build a runtime, I can build a signature for a module that is, there is some runtime rep. I don't know or care what it is. Tell me what it is, and I will build code peculiar to that runtime rep. This knows what the rep is. Now the problem is I have to instantiate this package. So it turns out if I instantiate the same backpack package with the same arguments, I get the same package in the package database. Therefore, two users doing the same instantiation would get the exact same hash, and it won't look like there's this nasty diamond worth of instances. The problem is what happens to my cabal file, or the first problem. So I can build this. I can build the ability to construct these definitions and put them into scope. Now when I go to build the mix instances, I start picking up a few lines of cabal. And it goes, and it goes, and it goes. And unfortunately, GHC starts to run into a problem with maximum Linux command line lengths. So this uses approximately 2 megabytes per command line for several thousand commands. It takes several hours to compile, but it did work. There was a couple of extra lessons I did learn along the way that I want to hit really quickly, and then I will happily yield the floor. Okay, the first one was, so let's go back to our classes. So I can do eq, that works fine. I do ord, it works fine. We just have these extra defines in terms of these default definitions you have to import once. We can do num. As a matter of fact, it works perfectly fine with GHCI. You have to disable the memorization of what the last result was, because that assumes that it was in kind star. Type, sorry. I saw the look of disapproval. So you have to disable it tracking, but other than that, it works. And with that, I can turn on rebindable syntax and add 1 + 1 at type int hash. Okay? There is a problem, but we can fix it. The first problem is that rebindable syntax is all or nothing. If you turn on rebindable syntax, you have to rebind all the syntax. And one of those pieces of syntax is if then else. So I lose access to if then else, or do I? So here's a thing that I found to work around most of the limitations about levity polymorphism, which is that while I can't take an A in negative position, I can take a unit double arrow A in negative position, because that is a computation that will return an A. Now, I'm not saying a function that returns an A. I'm saying an arrow from unit as a constraint to A. And so this is an action that takes an empty, no dictionaries, and then turns around and calls you back with A. And so when I go to build if then else, I can write it once and for all, and it works. Now what's important is this also has the correct semantics for if then else, because if you go to do if then else at a runtime representation that isn't lifted type, you don't want to evaluate the X or the Y until you know whether you're true or false. You only want to execute the one you use. Fortunately, that's exactly what has to happen here. It gets delayed until it gets invoked. And the unit is sort of happily applied for you. So I just wanted to say, please don't fix it so that I can't have a unit arrow as an actual thing in GHC. This does lead to some very interesting things. I can build completely unboxed natural numbers where we have the, just the tupling of the things to make up. This was before we had unlifted data types. So I had to use unlifted sums and unlifted products to make everything. But we can actually build some number types that actually get some pretty good performance, and I can actually push right up to the edge of what one could theoretically do. Is this a good idea? No. But we can do clever things with it, perhaps excessively so. Let's derive maybe in such a form that it works over all runtime reps as arguments. And we have to dip into using that same levitation trick in order to be able to switch runtime reps without having to have an instance for every pair of runtime reps in order to be able to do the mapping. So this trick, this levitation trick, was really the only thing that made this possible. And so I wanted to showcase it in case anybody ever runs into something similar, and wanted to make the case for this backpack piece. But in particular, this really calls for something that is missing in GHC, which is I am stuck doing the job that a C++ compiler has been able to do for me since the Stone Age, which is to basically instantiate a template and then deduplicate the instantiations, right? Theoretically, if what we were to do was to put the equivalent of a template keyword that I could use for runtime reps or really anything in type that had to be grounded out and would be generated by that code module, that would be deduped by the linker using the exact same linker flags that we use in C++, then the compiler could do my damn job for me. I could shed 3,000 lines worth of cabal file and several billion lines, or billion characters worth of command line. So please, God, I am begging for some way to get the compiler to do this job for me because I never want to do this again. Thank you. Any questions or? Anybody had anything? I'm happy to answer.
Have you considered using staging? So you take a runtime rep and return code of A to bool.
Yes, unfortunately, that doesn't make good libraries, though, right? Like the problem is like I want to, at the end of the day, have something that like participates in the type class ecosystem like everything else.
Yeah.
And it just leaves me a second-class citizen. Oh, and I can use a GHC plugin to achieve some of the goals, but I can't do the list and maybe constructions that I do. I can only do the type class extension.
Okay. Doing what? Oh, okay, thank you. Great, I'm Michael Adams. I'm presenting work that was actually done by a student of mine for his undergraduate research. Unfortunately, he couldn't be here, but most of the research is his work in this regard. I'm just presenting it. Okay, so, and a lot of this also is going to be talking about, while it is focused on the performance of parsing in GHC, I will be highlighting some tools that already exist that we found were very useful in diagnosing some of these things. Okay, so why are we talking about parsing in GHC? Well, the fundamental problem is that the current way indentation is specified in Haskell is rather non-extensible. For example, if you look in the spec, the way it's defined is that the lexer recognizes these 4 and only these 4 tokens as particularly special. What's even worse is that in between the lexer and the parser, we have to add this L function, which has about a dozen different cases, a little bit difficult to reason about, and even worse, we've got this parse error t function that's in red that calls into the future, into the parser, and asks, if I were to omit this token, will this generate a parse error? Oh, it will? Okay, then I'll omit this other token. So there's actually a cycle between the L function and the parser function. And in practice, GHC does not use this L function. Instead, it involves sharing state between the lexer and the parser. So I addressed this problem about a decade ago, dealing with a more compositional way to express indentation rules. And with this system, all you have to do is add annotations here in red that specify that, oh, for this particular region, we are starting a more indented region. The vertical bars represent that these have to be aligned. And there's a whole calculus that goes with this. If you do these annotations, you can then follow through the LR construction, and we even ported this into an experimental version of Happy that supported these annotations. And we were able to demonstrate that this works in practice. Okay, so well, what's the problem? The problem was performance. Now this is, number one, this was research quality code. So we weren't attempting to get like lightning fast performance. We were just attempting to demonstrate that it works. But nevertheless, it did mean that your parsing time approximately doubles. And that doesn't sound too good. That doesn't, especially if we want to eventually get this upstream. However, I should note that this is the parser time doubles, not the entire compilation pass time doubles. So the question for a long time was, well, what percent of time does the existing parser take? If the existing parser takes 30% and I double your time, well, I've just added a 30% overhead. If it's 10%, I've added a 10% or 1%, 1% overhead. Which of these universes do we live in? Well, when my student got interested in looking at this problem, initially I thought we'd have to be like benchmarking GHC and adding all sorts of different things. But it turns out there's already a library that makes this very easy to use. And so part of this talk is sort of advertising that library. Even if you're not doing parsing, this might be a useful library for what you're doing. And you can't really read it here, but what this library does is it uses the existing dedump timings flag in GHC, and then it extracts and generates some nice graphs where each line here is one of the packages within a build, and each of the different colors represents one of the passes. So the blue there is the simplifier, the green, I believe, is the code generation, and on the end, one of those small slivers is parsing. Now, of course, looking at it this way is a little bit difficult to get good statistics, so we did a little bit more data processing, and we're able to collect data on the 20 most dependent upon packages within Hackage, and we were able to get these results. And you can see pretty quickly that for small modules, that compile quickly, parsing does represent a significant amount of the time, but for larger ones, it's a much, much less amount of time. If we change the axes to both be logarithmic, it's a little bit easier to see that there's some sort of a power law going on here. In fact, because the best fit is a square root, I suspect what is happening is that something else in GHC, not the parser, because the parser should be linear, something else in GHC is going quadratic. And so there's something going on in GHC's general performance. The median performance then becomes, that's the green line, of 1.73% of time is being spent on parsing. So if we were to implement this indentation-sensitive parsing, maybe you expect that much of a slowdown, except that this median is weighting all packages equally. So if I have 10 packages that each take 1 millisecond and I double their time, versus one package that takes 100 milliseconds and I increase this time by 1%, those 10 packages are going to outweigh the one major package. So we did some aggregation instead of at the module level, at the package level. That then brings the median down to 1.6. Of course, if you're doing an entire application, we shouldn't be really looking at the package level. We should combine them all together, in which case the median is only 0.73%, or 0.7% of time is being spent in parsing. Okay, main takeaways. dedump timings and time GHC modules are cool. They saved us so much effort, and if you're doing anything where you're like, I'm going to add this feature, will it hurt me? Where's the cost going? I absolutely recommend taking a look at those. We did some extra processing to aggregate numbers, and you can probably port that to other things beyond parsing. The code for that is available. We also packaged up the Happy prototype, which has been around for a while, but has never been merged upstream. So if someone is interested in taking that work from research quality code to production quality code, and maybe eventually we can get this into mainstream Happy, I would be very interested to talk with you, because I think this might be something that will enable a more extensible language. Like if we wanted syntactic macros in Haskell someday, we need some sort of a system like this. All right, thank you. Oh, and by the way, I do have multiple PhD and postdocs available, so if you're interested in improving language ergonomics, for example, a language where making GHC more extensible, please come talk to me and we can maybe collaborate. Thank you.
Okay, thank you. Can you hear me? Good. So I'm going to show you a little demo that I like, a little bit of fun I've been having. Some of you, a few of you may have seen it before, but I hope that most of you will not have done. So every now and then, I like to play with alternate random generation libraries. So surprise, surprise there. So here's an example, and I've got a little demo of a library called rgen. As you can see, it's just choosing some numbers and returning them in a tuple. So I just to set the scene, I want to show you that in action. So if I reload, that's good. Now I can just pick a random value, and you know, as you would expect, I'm picking 6 random numbers each time. Okay, so that's very unsurprising. This is exactly like random generation and quick check. What's interesting about this library is that I can also add some constraints. So let me just constrain, let's constrain A to be equal to F, say. Okay, so if we do that, and I reload, then, well, you know, the first and the last values are always equal. So I just want to emphasize here that there's nothing funny going on here, right? This code does what it looks as though it's doing. Those are ordinary integers. That's ordinary Haskell equality. We are actually, this is working by generating about 100 test cases and throwing them away, and then ending up with the one that has equal first and last elements. So only 1 in 100 generated test cases is actually valid and passes the guard. But as you saw, it doesn't matter. Computers are fast. So that's okay. Let's see how far we can take this. What if I require B to be equal to E? And while we're at it, let's require C to be equal to D. Okay, so if I reload this, now they're palindromes. Whoa. 1 in a million values passes those guards, but look, it's still pretty fast, isn't it? Computers are fast. All right, let's see whether we can go further. Let's require, maybe A and B to be equal. Let's require B and C to be equal. You don't like inequalities?
It's more fun with equalities. Let's just reload that. Oh, okay. There we are. So now all 6 values have to be equal. There are 100 satisfying values in a million test cases. Computers are fast, but they're not that fast. Okay, let's take C. Okay, so what's going to happen here? This is harder. We selected the only one of a million test cases that passed the constraints. Are your jaws dropping? Mine did.
What if you put the C equals 42 first, John?
If I put C equals 42 first?
Would that constrain it? So that
Let's try it. Okay. It's still the same, yeah.
I'm impressed with that.
So I could have put inequalities as well, but they're less of a tight constraint, so it wouldn't have made the point the same way. So what's going on here? How can this possibly work? Well, let's look at
the code of the generator. What's going on here? Oh, good. Here is the generator type. So generators are just trees. They can fail. That's the new possibility compared to quick generators. They can deliver a value, or they can make a random choice. And that rational there, that's just the probability of choosing the first branch. So there's nothing funny there. And we can make them into a monad, of course, which you have to do. And here's the code for that. So if the first argument is a failure, then we fail. If the first argument delivers a value, then we just pass it to the second argument. And if the first argument makes a random choice, then we make a random choice. Now, that is exactly the code you would expect to write for this representation of generators, except for the blank line after the first clause. And sure enough, I'm going to put something there. Okay, so before we start before we start exploring the randomness in the first argument, if the continuation h fails in any case, no matter what we pass to it, then we fail immediately. So you might have been a little suspicious of this is-fail function. What is that? It's the secret sauce. That's where the unsafe perform IO is. Okay, so all that is doing is inspecting x. If x is fail, we say true. If it's something else, we say false. And if it's an exception, you can see that I've passed in an exception to h, then, well, we don't know that it's fail anyway, so it returns false. And we do not prune the search space. So the effect of this is just that the order in which I write those guard clauses doesn't matter at all. So you asked me for that, Kevin, and you saw it didn't make any difference. And the reason is because this bind operation fails whether it detects a failure in the first argument or in the second argument. So as soon as there's any guard in the continuation that fails regardless of the choices of some of the values of the other variables, then we can fail early. And that pruning leads to this very fun behavior. By the way, this is exactly the same trick that lazy small check used to prune its search space. All I've done, though, is I've applied it to random generation instead. There we are. That's what I had for you. It's fun, isn't it?
Is that kind of like cut?
No, it's not, because cut may actually throw away answers. Here, we're not throwing away any answers. We're pruning parts of the search space that we know can never succeed. Yes, it does actually. That maybe that's important. I haven't tried the other thing.
Does this approach mean you'll be evaluating h twice? And how do you keep that from blowing up exponentially?
It does mean you'll be evaluating h twice. It seems to work anyway, I think, because you usually hit that exception early on when you call h the first time. And so in practice, it doesn't really seem to be exponential. It is very easy to break this code, though. I have broken it in so many ways. But in its present form, it works fine.
Just a shower thought, but could you use these kind of fancy new delimited continuations that we have to, if it fails, then like pick the value and resume rather than retrying from the start?
Pass.
Okay.
As I say, it's easy to break this. I wondered for a while whether I could detect using the argument by writing to an IO ref. And that doesn't work at all, because that detects the first use of an argument, and it means basically that you can prune too much because you don't detect later uses. So there are many ways to break this. And it's difficult to promise that any other approach would work without trying it. Thank you.